Bismillahirrahmanirrahim. Assalamu alaikum dear students. This is our next problem having been chosen from the book Modern Physics by Kenneth S. Gray. As usual, we first come to its statement. Okay. At what temperature do the lattice and electronic heat capacities of copper become equal to each other? Take TD, where D is written as a subscript of T, is equal to 343 Kelvin, and E capital E capital F, where capital F is written as a subscript of capital E, is equal to 7.03 electron volt. Okay, dear students, here TD is Debye temperature. DEBYE, Debye or Debye is the scientist name. Okay, for the time being we have nothing to do with the detail of this name or scientist. Okay, for the time being we are our primary concern is just to solve this problem. Okay, so TD stands for Debye temperature. D for Debye or Debye, DEBYE, Debye. D for Debye and T for temperature. Okay, Debye temperature equal to 343 Kelvin. Dear students, when we temperature in Celsius or centigrade or Fahrenheit, then we use the term degree, but when we use the temperature in Kelvin, we do not use the term degree. Okay, so here Debye temperature is equal to 343 Kelvin, and E capital F, where capital F is written as a subscript of capital E, is Fermi energy. Fermi is also scientist name. Okay, for the time being we have nothing to do with the name of scientist or its detail. Okay, our primary purpose is just to solve this problem. Okay, at what temperature do the lattice and electronic heat capacities, okay, one type of heat capacity is lattice, which is also called as a Debye heat capacity. Okay, and other is electronic heat capacity. Okay, two types of capacities we have to determine. Okay, lattice or Debye heat capacity and electronic heat capacity of copper. Okay, at Debye temperature 343 Kelvin and Fermi energy equal to 7.03 electron volt. Okay, now we come to helping tools. Okay, dear students, first helping tool is about Fermi energy. Okay, in this table, in this tool we will show table in which Fermi energy of various elements is given. Okay, so here dear students, because copper is under consideration, so here 1 2 3 4 5 6, at row number 6 Cu 7.03 electron volt. Okay, so Fermi energy of copper, that is its Latin name comes from cuprum, Cuprum, that is why it is denoted by Cu. Okay, copper, cuprum, Cu, Fermi energy 7.03 electron volt. Okay, now its alternate version is shown. Okay, that is to say this type of snapshot has been selected from some other book. Okay, in which Fermi energy of various elements is given. Okay, in this table 1 2 3 4, okay, at serial number 4 copper or cuprum Fermi energy is given as 7.05. Okay, in previous table, that is in its alternate version, this energy, Fermi energy, was 7.03. In this table, it is 7.04. Okay, so not a substantial change, not substantial difference. Okay, and let us see another version of this helping tool. Okay, that is Fermi energy of various elements. Okay, in this table, copper, yes, okay, 1 2 3 4 5 6, at serial number 6, copper Cu is given at 7.04 electron volt. Okay, so dear students, here we have shown three versions in which table is shown in which Fermi energy of various elements is given. According to these various versions, Fermi energy of copper according to one table is 7.03, according to other table is 7.04, and according to third table it is 7.05. Okay, so it does not make any difference. It is quite acceptable. Then, dear students, another table is shown at helping tool number 2. A comprehensive table of physical constants is shown. This table has been included in our problems or in our videos several times. So for the time being, we do not give any further time to this table, because this table has been taken into consideration several times. Now, dear students, third helping tool is about electron contribution to heat capacity. Okay, electron contribution to heat capacity, C is equal to pi square K square, K, where K is Boltzmann constant. Okay, Na stands for Avogadro's number, T for temperature, divided by 2 Fermi energy. Okay, this alternatively becomes equal to pi square capital R. Capital R is gas constant or universal gas constant. Okay, then again K, that is Boltzmann constant, and then T, temperature, divided by 2 Fermi energy. Okay, helping tool number 4, Debye heat capacity or lattice heat capacity. Okay, Debye heat capacity, C is given by, C is equal to 12 pi raised to the power 4 divided by 5 into capital R, that is gas constant, or more commonly known as universal gas constant, into temperature 2 over Debye temperature, whole raised to the power 3. Okay, dear students, here actually in tool number 3 and tool number 4, it is written that 11.12. Actually, this is not equation number 11.12, 11.2. Okay, because one equation cannot be repeated twice under the same number. Actually, this expression is given in the book Modern Physics by Kenneth S. Crane, and such expressions are given in summary at the end of a chapter. Okay, so these two tools, that is tool number 3 and tool number 4, belong to second topic of 11th chapter. Okay, so I want to clear that this is not equation number 11.2 and then again 11.2. It indicates that this is second topic of chapter number 11. Okay, both tools, tool number 3 and tool number 4, belong to second topic of 11th chapter. Okay, now we come to its solution. We know that electron contribution to heat capacity is, okay, C equal to pi square into capital R, universal gas constant, into K, Boltzmann constant, into T, temperature, over 2 EF, that is Fermi energy, equation number 1. And Debbie heat capacity is given by C equal to 12 pi raised to the power 4, where pi is equal to 3.14. Okay, 22 by 7, according up to two decimal places it is 3.14. Okay, 12 pi raised to the power 4 over 5 into universal gas constant capital R into temperature T over Debbie temperature raised to the power 3. Okay, equation number 2. Okay, now equating equation number 1 and 2. Okay, because both are heat capacities, both are equal to C, so we can equate right hand side of both equations. Okay, now equating equation number 1 and 2, we have pi square into universal gas constant capital R into Boltzmann constant K into temperature T over 2 into Fermi energy is equal to 12 into pi raised to the power 4 over 5 into universal gas constant capital R into temperature T over Debbie temperature T TD whole power 3. Okay, this implies that pi square capital R K over 2 Fermi energy into 5 over 12 pi raised to the power 4 into Debbie temperature TD raised to the power 3 over capital R is equal to T square, and hence this implies that from here when we take under root of both sides, then in place of T square we will get the value of simply T becomes equal to 5 into Boltzmann constant K into Debbie temperature TD raised to power 3 divided by 24. Yes, because 12 into 2 equal to 24. 22 pi square, because in the numerator there is pi square and in the denominator there is pi raised to the power 4. So in this step pi 4 in the denominator has been reduced to pi square. Okay, into Fermi energy EF is equal to 2. This is equation number 3. Okay, now we will put conserved values in this equation number 3. Okay, so taking Boltzmann constant K equal to 8.617 into 10 raised to the power minus 5 electron volt over K. Dear students, this value is given in the tool in which we showed a comprehensive table of physical constants. Okay, moreover, Debbie temperature TD, where D is written as a subscript of capital D, capital T is equal to 343 Kelvin. This is given in the statement. Okay, moreover, Fermi energy EF is equal to 7.03 electron volt. This is given in this statement. Okay, not only it is given in the statement, but also we have confirmed this value from our helping tool, in which this value has been shown in 3 alternate versions, in which 3 tables were shown, in which Fermi energy of various elements were given, and according to these 3 tables, Fermi energy of copper according to one table was 7.03, according to the other table it was 7.04, and according to third table it was 7.05. But here, because it is given in the statement as 7.03, so we have taken the same value which is provided in the statement. Those 3 tables were just to make a comparison or to develop a confidence that even if such value has not been provided in the statement, then we can consult such tables and find the value. Okay, moreover, value of pi is equal to 3.14 up to 2 decimal places, which is actually 22 by 7. Okay, and we know that decimal representation of pi is non-terminating, non-repeating. Okay, it goes endlessly. Okay, so putting all these values, we get the value of T equal to 5 into Boltzmann constant K into Debbie temperature TD raised to the power 3 divided by 24 pi square into Fermi energy. Okay, This becomes equal to 5 into 8.617 into 10 raised to the power minus 5 electron volt over Kelvin into 343 Kelvin raised to the power cube divided by 24 into 3.14 into 3.14, because pi is in square, into 3 into 7.03 electron volt. Okay, dear students, here electron volt will be cancelled with electron volt, and 1 Kelvin will be subtracted from Kelvin cube, and hence we will be left with Kelvin square within the under root sign. And when it will come out of the under root sign, then it will, this Kelvin square will become simply Kelvin K. Okay, so simplifying this expression goes to T equal to 12.45 Kelvin square within under root. Okay, under root, and taking under root of this value, T becomes equal to 3.23 Kelvin. Temperature T equal to 3.23 Kelvin. T equal to 3.23 Kelvin. This is the end of our problem. This is the end of our video. Till next video, Allah Hafiz.